Hi everyone, and welcome to your Friday pre-recorded lesson. I want to start today off by taking a look at an example that's similar to that subtraction that we did on Wednesday, but maybe just has a little bit of a twist to it. So what you'll notice here is this subtraction is 3 1/4, and we're going to try to take away 1 3/4. Now, if we try to set this up and execute it in a way that's similar to what we did last time, and that would be to take our 3 1/4 and try to take away 1 whole and take away 3/4. We can regroup all of the wholes together like this, but we're kind of going to get stuck here with this subtraction. So we're going to run into a problem along the way. So let's take a look at the model and see how we might be able to use the model to help us out here. So we're going to model the minuend, which is 3 1/4. So here's our 3 wholes. And let's divide our last shape into quarters. So we have 3 1/4. So what we want to do now is take away our 1 whole and take away our 3/4. Now we can take away the 1 whole relatively easily, right? I can take that away. That's fairly straightforward. However, I'm going to run into a problem because I have 1/4 and I need to take away 3/4. And right now, nothing else is in quarters. I just have that one singular quarter. So what we actually have to do here is we actually have to kind of go into one of these other holes that we have and break it down so that we can take away the 3/4 that we need. So in gray, I'm going to go ahead and I'm going to take away 1, 2, 3/4. And then I'm going to go ahead, I'm going to draw what's left over for us. Then we'll see if we can kind of interpret this over on the left-hand side. So we have 1 whole that was not affected whatsoever. We had 1 whole that was taken away. And then we had 1 whole that we had to break down into quarters in order for us to take away 3 of them. And so what we have left is we have 1 whole, and it looks like 1/2, or 1 whole and 2/4 left. So what the heck happened over here on the left-hand side with our numbers? Well, we are able to do the 3 take away 1, that's 2, and then we run into a little bit of that situation here, right? I have 1/4 and I don't quite have enough quarters to take away 3 of them. So what we actually had to do was break apart one of these holes into quarters. So we essentially took this number 2 and we rewrote it as a whole plus 4/4. And you can see that right up here in the picture, right? So when we took that those original 2 holes, we took one of those holes, broke it up into quarters, into 4/4, and that allowed us to take away 3. And when we broke up our 1 whole into 4/4, how many quarters did we have? We actually had 5/4. So this is kind of like heading over to the bank, borrowing a little bit of money so that you can pay off those debts. It's kind of the same thing. We kind of go over to our whole number. In this case, we had to borrow a little bit from one of our whole numbers so that we could take away 3. And so what we can see now here up top is we have those 5/4 highlighted right here. So it's our 5/4, and we took away 3 of them in gray. Okay, and that left us over with 2/4, and we can see that here in our updated model. Okay, so we had 1 2/4 left over. And of course, if we want to simplify this, we could simplify this to 1.5 as a final answer. I am being silly today, and I am obviously forgetting all of my equal signs, but yeah, there should be some equal signs running down the side of the page here for us. So that's kind of, if we want to approach it in a very similar kind of way to what we did on Wednesday, we run into that problem of needing to break apart one of these whole numbers in order to do this subtraction. There is, however, a secondary way to tackle problems like this, and I'll show you way number 2. And this is what a lot of textbooks might suggest students do as well. So this is saying 3 1/4, take away, I think it was 1 3/4. And a lot of sites I've seen will do the following. They'll say, well, I'm dealing with a subtraction of mixed numbers. I have this potential issue that I might run into of needing to borrow from one of the existing whole numbers. I don't really want to run into that issue. So what sometimes is done first is sometimes we convert this into an improper fraction. So for our first fraction, we have 3 wholes, which is 12/4, plus our remaining 1, so this would be 13/4. And then for our second fraction, we have 1 whole, which is 4/4, plus our extra 3, so this would be 7/4. And so now, since we've converted into an improper fraction, we have the capacity to do this subtraction without having to go and borrow from one of the whole numbers. So essentially, if we were looking at a model, it would look something like this. We'd take our original 3, 1, 2, 3, 1/4. And essentially what we're doing is we're automatically taking those 3 whole portions and breaking them down into quarters. So the first step would actually be just breaking all of these whole portions down into quarters and adding up how many of those I have. So we could say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is where our 13/4 comes from. It comes from breaking those 3 whole portions into quarters. And now we can take away 7/4. We could even now probably take away 1 3/4 if we wanted to as well. We don't really need to convert that second fraction, but I convert it just for the ease of being able to take stuff away. So now everything is in quarters. I can go and I can find 7 of these things. So 4, 5, 6, 7. So let's take these away. And what we're going to be left with is 1, 2, 3, 4. I think we're going to be left with 5. So all of these 4 at the top haven't been affected. Oops, I'm sorry, there should be 2 more here. 1, 2, because that one is shaded in down here. So I'm just going to go and I'm going to highlight the 4, 5, 6 that are left over. That's what we're getting down here in our updated model at the bottom. So 13 take away 5 would give us 5/4. And then we could go through the long division procedure if we needed to convert this into a mixed. This should be 6/4. Try again. Into our mixed number. So we convert this into a mixed number. We would have 1 2/4 or 1 1/2. So that's way number 2. So just in case you run into these kind of trickier subtractions, you can convert everything into improper fractions and then deal with the subtraction in a much more kind of straightforward way without having to use that regrouping or borrowing method. So that was the harder subtraction that I wanted to show you. And I wanted to show you both ways to tackle that kind of problem. It can be done without having to resort to improper fractions, but typically we show students how to do the improper fraction method because it does work all of the time. It's a pretty much 100% guaranteed you're going to end up with, hopefully, as long as you can do your subtraction properly, the correct final answer without having to do this awkward borrowing step. Okay, so with that said, let's keep on diving down the rational number rabbit hole. And what we're going to do is we're going to take a look at a couple properties of rational numbers as well, just so that we have them in our notes. Now, some of these are going to be fairly straightforward. We have talked about some of these already. So the set of rational numbers is closed under all 4 of our major operations. It's not closed necessarily under exponents, though. So I'll just kind of maybe pique your curiosity a little bit. We are going to talk about this soon when we start talking about what a fractional exponent might mean and what that looks like. But it's quite possible that we could take two rational numbers. We could apply one to the base, and we could apply a different rational number to the power, to the exponent part. And we could maybe not get a rational number anymore. We might get something that's not expressible as a fraction. And this essentially is what leads us to the final number set where we kind of combine everything together. That's the real number set. So yeah, so just be mindful of that. Taking exponents could get us into a little bit of a pickle because at the moment we don't really know how to deal with a fraction that's inside the power. So what does something like 2 to the power of 1/2, what does that even mean? What does that look like? Is that a rational number? We're going to see that that's not. So, I mean, other than exponents, which is its own little bag of worms, the rational numbers are quite nice. They're closed under all of the major operations that we work with for our elementary and middle school students, maybe barring taking exponents. Okay. Addition and multiplication do remain commutative in this set. And of course, subtraction and division, being the stubborn operations that they are not going to be commutative with rational numbers. However, we did talk about this really interesting property of subtraction. So if I think about two numbers getting subtracted, 7 take away 1 is 6. And if I try to commute the order of those things, I end up getting the opposite. So that was an interesting kind of property with regards to subtraction. Now, with regards to division, I mean, the same kind of thing happens. If I try to do 12 divided by 4, for example, I'm going to get 3. But if I do 4 divided by 12, we can view this as a fraction, which is 4 over 12. And we could put this into reduced or lowest form of this fraction, which would be 1/3. So there is an interesting relationship between performing this commutative kind of operation with our numbers. We do end up getting something called the reciprocal. That is the relationship between the two numbers when we try to commute over division. Okay, so of course reciprocals meaning taking the fraction and putting it on its head, essentially. So we get, we get 1 over that number if it's a whole number, or if it's a fraction with a numerator and a denominator, the numerator and denominator actually switch places. So this is the idea of reciprocal. So that's the relationship between trying to commute numbers with regards to division. But of course, we've talked about order of operations and thinking about subtraction as adding the opposite number. You can also think about dividing as multiplying by the reciprocal of the number. And that allows us to do some of those commutations that we did in the last chapter. Okay, so let's talk about identity. So the additive identity is still 0. And the multiplication identity is still 1. The only new thing that we have is not only do the set of rational numbers contain the opposites of all of the positive numbers, they also contain the reciprocals of all of the numbers as well. So not only do we have additive inverses These are called the opposites generally. We also have multiplication inverses, and we tend to call these the reciprocals of our numbers. So we've talked about this one already with regards to the set of integers. The opposite numbers, basically we're just multiplying that number by -1 to get the additive inverse. And now all of our numbers, except for 0, 0 is the only kind of fussy one here in the set of rational numbers, but all numbers except for 0 have a reciprocal. So let's take a look at a couple examples here. So if I take the number, I don't know, -2/7. So -2/7 is not 0, so it should have an additive inverse as well as a multiplication inverse. A multiplicative inverse is what we say. So the additive inverse is the opposite. Additive inverse is the opposite, so 2/7. And I can double check that I have the correct additive inverse by actually adding them together. If I add these two numbers together, I should get to the addition identity, which is the number 0. So that's how you kind of can double check this stuff. So that's the addition identity. So like I said, I always think about the additive inverse as the opposite of the number. So the number I get by multiplying by -1. Now the reciprocal, or the multiplicative inverse, I can spell that in a very small way, is going to be what we call the reciprocal. So it's the number that we get by exchanging the numerator and the denominator. So in our case, we get -7 over 2. Now note here that it doesn't matter where I put this minus sign. I could keep it with the 2. I could put it with the 7. Generally what we do is we keep those negative signs inside the numerator. So I mean, if you put it down with a -2, it's not a big deal, but we usually just keep it with the number inside the numerator. Now this is the multiplication inverse. And the multiplicative inverse is set up in such a way that when we multiply these two numbers together, we get the multiplication identity. So -2 times -7, that's going to give us +14, and 7 times 2 is going to give us also +14, and we do see that we end up getting the number 1, which is the multiplication inverse. Or multiplication identity, sorry. So that's how multiplication inverses work. We basically take the reciprocal, and it's the number that when we multiply the original one, we get back to the number 1. Now, because we're taking reciprocals, we're swapping the order of the numerator and the denominator. 0 doesn't have that reciprocal because I would have to take 0 divided by 1. 0 over 1 is the fraction. Swap the order of 0 and 1, and then 0 ends up in the denominator. And unfortunately, then I don't have a rational number anymore. I have something that's undefined. So 0 is the only one that doesn't have a multiplication inverse. And it kind of makes sense, because if I try to ask myself, what would I have to multiply 0 by to get back to the multiplication identity? Well, there's no real number that I can put in here to make that work, right? 0 times anything is equal to 0. So I can never make this equal to 1. So 0 doesn't have a reciprocal. It does not have a multiplication inverse. So maybe just worthwhile to note that here. Sorry, chores day. So apologies if you Got a little distracted by the vacuum cleaner there, but let's see. That should take care of most of the big properties. So last up is what we call the well ordering principle. What number are we at here? And the well ordering principle essentially just guarantees that for all of our fractions, we have some kind of form where we can't really factor out any other common factors. So what do I want to say? So every rational number has a unique representative to a fraction of the positive denominator. Yes. Don't actually care about that. So let's talk about this last bit of information here. So let's say every rational number has a unique representation and often we call this unique representation the lowest form fraction. Okay, so a unique representation that we call the lowest form fraction. This lowest form fraction is what we call irreducible. So it means that we can't factor any other common factors out of this fraction. Okay, so it's the lowest form fraction, well, irreducible fraction with a positive denominator. We're going to assume that that denominator is always going to be positive so that the negative, if we have one, is up in the numerator. Okay, so let's talk about a couple words here. So there's a couple of things I just want to kind of make note here. So irreducible, like I was saying, means that maybe we can factor the numerator and the denominator into like prime powers, but none of those prime powers are ever going to cancel. So this is what I mean by irreducible. The numerator and denominator will not share a common factor. The only one they'll share is the number 1. Okay, so they share no common factors that are larger than the number 1. And this idea here of having a positive denominator basically just means that we're going to, if we have a negative sign, it's always going to go up into the numerator. So negative signs always bumped up into the numerator if we have them. I don't think that's like super necessary to be like forceful about, but it does make things look a little bit cleaner and makes sure that like when you're doing computations and stuff like that, you can see that negative sign really easily. So I would say it's just more so common practice. Okay, so those are all the big properties. I do want to maybe explore this last property just a little bit more to make sure you're comfortable with it. And that's probably going to be what we need to cover for today's class. So let's work through a couple examples of doing this reducing fractions so you can get a kind of idea of a technique that you can show your students if this is something that you would like to do. I mean, there are a lot. I mean, our calculator, I mean, you can program a fraction and it's going to reduce it for us. But I think if you want your students to practice certain techniques, it's not necessarily a bad thing to ask them to practice prime factorization and use that technique to reduce these fractions. So it's one way of utilizing some of our past techniques to kind of refresh their memory on some of those past techniques. So let's take a couple examples to finish off. Let's look at the fraction. Oh, goodness me. Okay, let's make up a fraction. Let's go 30. This is also why we probably use the word reduce. I'm going to say find the lowest form of the fraction. So find the fraction's lowest form. And again, I don't think there's any good way of actually saying this out loud other than we're looking for the representation that's irreducible. It's the one that doesn't share any common factors. I think all of the other wording that we use is actually a little bit misleading because when I see the word lowest inside of lowest form, it makes me think that one fraction is smaller than the other fraction when really they're the same. They represent the same proportion. So yeah, I find the terminology a bit funky and I don't like it, but you know, we have to live with it, unfortunately. That's just the way that it is. So first fraction, let's go 30 over well, maybe not that big. We can take out one of those factors. Let's go 462. Okay, so I got this big old fraction. I got 30 over 462. How in the world am I going to reduce this fraction, or how am I going to find the irreducible fraction that's the same proportion as this one? Well, the main technique that you can use if you don't have access to a calculator that'll do this quickly is we can start factoring this. Now we can blindly factor this, which is sometimes helpful. So for example, I can look at the number 30 and look at the number 462 and see if they share some kind of common factor. I mean, it looks like they share a common factor of 2. So for instance, I could divide both of these by 2, which would be 231. So that's a possibility. Let's actually maybe work our way through that case. So you can see how I might write some stuff down. I think that was 30 over, 462. So what I've often seen teachers show students is to do something like this, right? You can actually do a division like this, and that way you can kind of follow along with what the student's thinking and double check their work and try to find their errors a little bit easier. So here I know 30 divided by 2 is 15, and I know that 462 divided by 2 is going to be 231. Okay, so from here it's not super obvious without maybe a little bit more work. I know that 15 is divisible by 5 and by 3. I know that 231 is not divisible by 5, but we could check to see if it's divisible by 3. So let's just kind of quickly check that. I believe that's going to work in our favor. 2 plus 3 plus 1 is 6. So we know that this one is divisible by 3. So we could divide both of these by 3 as well. 15 divided by 3, we know that's 5. And 231 divided by 3 is going to be 77. That's fun. And so now I have the irreducible fraction that's equivalent to the one that I started with. It's the same proportion as the one I started with. It just doesn't share any common factors anymore. So 5 is a prime number. 77 is not divisible by that prime number, so there's no way that I could reduce this fraction any further. This is what we call the lowest form of that original fraction. So this is what I mean by the ability to reduce. And if you want, you could even go that one step further and, you know, throw in some large numbers. Like we've dealt with some kind of tame numbers. They're not too hard to work with, but let's get a little crazy and let's actually do a really large, work with a really large fraction here. So 1332, and in the denominator 79992. So in this case, I suspect that maybe these two numbers might share a common factor that's bigger than 2. And I don't want to sit here and be dividing by 2 for like 15 minutes until I finally get to the irreducible fraction that's equivalent to my original one. So one method you could use is to actually think about prime factorization. So we could take our 13332 and start making a factor tree for it. This is just kind of over on the side. So let's see, 3, this is divisible by 3, certainly. 3, 6, 9, 10, 11, 12. So what if we divide this by 3? What would we get? Oops, let's divide that by 3, and we get 4, 4, 4, 4. Now 3 is a prime number, so let's kind of focus on dividing this by 4. And 4 is going to break down into a pair of 2's for us. So we're going to be stuck with this number 1, 1, 1, 1. Now I suspect that that's divisible by 11, so let's go ahead and divide that by 11. And I get the number 101. I know 11 is prime. I don't know if you guys know if 101 is prime or not. So what we could do is, we could jump over into Google and we could take a look at, 101, is it prime? People ask this question all the time. Is 101 a prime number? Yes. All right. So 101 is a prime number. Let's go ahead and let's circle that. And now we have an idea of what our numerator looks like in factored form. It's 2 times 2 times 3 times 11 times 101. So there's my numerator in factored form. Let's do the same thing for the denominator, 79992. And it looks like this one's actually going to be divisible by 9. So we have 7 plus 9 plus 9 plus 9 is 2. So this one should be divisible by 9. You can kind of double check by adding up. And let's divide that one by 9. So 79992 divided by 9 gives us, oh, interesting, 8, 8, 8, 8. That number is most certainly divisible by 8. And of course, 8 breaks down into 4 and 2. So we're going to get a bunch of 2's here. And we already know how this 1,111 breaks down. That's 11 times 101. And both of those are prime numbers. So let's write out our prime factorization for our denominator. It's 2 times 2 times 2 times 3 times 3 times 11 times 101. So now that I have these prime factorizations, actually I'll scroll up in case you need to copy something down there. We can kind of now scan through these numbers and cancel off any factors that the numerator and denominator share. So I notice, for example, that there's a common factor here of 2. I can remove that because these would divide out and give me the number 1. Same thing here. So this 2 would essentially divide out with that other 2 and give me 1. And I just kind of keep on trucking. So those 3's will divide out. This 11 will divide out. And surprisingly, the 101 is going to divide out here as well. So in the numerator, since everything is canceled out, we really are just left with the number 1. Inside the denominator, the leftover numbers are 2 and 3. So it turns out that our irreducible fraction that's similar to what we started with is actually 1/6. I find that actually a little bit funny that it worked out to be such a nice fraction. But I guess I should have been able to kind of suspect that based on the way that these two numbers looked. But that's one way you can kind of like harken back to like some of these old techniques, right? Like how are your students finding factors? Are they drawing a factor tree like we did? Are they doing some other method to find factors? Can they find the greatest common factor? If they can find the greatest common factor, so for instance, the greatest common factor in our first fraction would be 6. If you can find the GCF, you can divide the GCF out to get to the final answer right away. So that's kind of you can kind of harken back to some of these old techniques to be able to simplify or reduce as the terminology we use to get to this lowest form fraction. So hopefully that gives you a little insight into how we can use some of those old techniques to do some work for us. It just gives you that kind of quick and brief overview of the main properties. So a lot of them are still true. And one thing we want to kind of think about a little bit coming up here is how to deal with that exponent problem and how to extend this group of numbers out just a little bit more to deal with that problem of working with exponents. Cool. So with that, have a lovely rest of your weekend, and I'll pick up with you guys on Monday, where we're going to take a little look, especially at dividing rational numbers, because I want to work a little bit more with those two representations we saw in the division chapter. So we're going to bring back the measurement and the partitive models, and we'll try to see how we can utilize those when dealing with division of fractions, because division of fractions can get a little bit weird. All right, so we'll do that Monday. Have a lovely weekend, guys, and I'll talk to you soon.